Well, greetings, mathletes, and welcome back. Today we're going to be learning about derivatives, and granted, we've already learned about derivatives. And as far as derivative techniques go, we've actually covered all the ones we're going to cover. What we're going to be looking at today, and like we did last time, and as we will in the next couple lectures, we're going to be looking at things that derivatives can tell us, basically. And so today what we're going to be covering what's called the first derivative test. I don't particularly think of it as a test. It's more like, I don't know, you just kind of lay things out and see what it tells you, really. But it's a way of of looking at the derivative and being able to tell something about the function itself, the function that derivative came from. And so this is all leading up to being able to sketch a curve, a fairly complicated curve. You did some of that in pre-calculus where you found the zeros of the function and things like that. You could tell what kind of zero you had, whether it bounced off the x-axis or whether it went through it, or things like that. Well, we're actually going to be taking that a little bit further, and we're going to be looking at how the derivative tells us about whether a function is increasing or decreasing today. So let's go ahead and take a look here. Okay, so what we're looking at here is a function f and the derivative of that function f prime. All right, let me just scoot this over just a hair. We'll get the whole thing in there. All right. Now, remember that what the derivative tells you is what the slope of the function is. So at this point, right here, if I pick that point, whatever this slope is, or whatever this function value is right here at this point, is the slope right here at the same point on the other function, right, on the original function. So here, the function value is between 2 and 3, and so the slope here would be somewhere between 2 and 3, whatever that number happens to be. Now, I'll get rid of some of this, clean this up just a hair. There we go. Okay, now, so what that means is anywhere the slope is positive, if the slope is positive, this thing is moving upwards, right? Everywhere here, the slope is positive. So over here, the slope is positive. How that shows up in the derivative is that the derivative is above the x-axis. So if I look at this, if I just draw a line here on the x-axis, right? These parts that are above the x-axis represent places where the original function is increasing. Anywhere that I have a negative, like this part, right, it's below the x-axis, those are the places that the slope is negative, right? And this is so easy to get this confused between the slope and the actual function value and all these different little moving parts in this. So you really have to mind yourself here. Because when we're talking about the derivative, it's the value at a particular point we're talking about. But if we're on the original function, it's the slope at that point we're talking about. So if I look at this, I can see that the derivative is below 0 right here, from x equals 0 to x equals 2, right? And if I go up here, what I can see when I go up to the top function here is that same interval from here to here, the slope of the function is negative. The tangent lines all have negative slopes. Over here on the outside, where it's positive, these all have positive slopes. And you can see it's increasing. If the slope is positive, the function increases. If the slope is negative, like in here, the function decreases. So what we can tell from this, just looking at the derivative, we can say, okay, so between 0 and 2, the slope is negative, which means the function is decreasing. But from negative infinity to 0, and from 2 to positive infinity, the function is increasing because the derivative is above the x-axis, right? So it's a matter of keeping those things straight. And I'm really hoping I keep all my words straight, because you keep going back and forth between the function and the derivative enough times, you start getting them confused. So I'm hoping I don't do too much of that, because I might trip over my words a little bit. Okay, so that's what we're actually after. So we could be given a couple of things. We could just be given the equation of the function, and asked where the function is increasing and decreasing. And so what that means is that we would have to take the derivative and figure out where the derivative is positive and negative, right? And those division points, those points between positive and negative, are actually critical points. And we found those before by setting the derivative equal to 0. Because what has to happen is if a function, particularly the derivative in this case, if the derivative goes from being negative to being positive, it had to cross a 0 in there some point. So the zeros are going to be how we figure out where these regions are as we go through this. And so now that we've looked at this graphically, I actually want to give you the equations of these functions, or this function, right? So f of x is equal to, what did I choose? Yeah, it was x cubed minus 3x squared plus 2, right? And so the derivative then, we can obtain that on our own even without being given this. All we have to do is just take the derivative. So that would be 3x squared minus 6x, right? And the 2 goes away. Okay, so if we want to figure out what the division points are, where the derivative is positive and negative and stuff, we start out by finding the critical points. And we find critical points by setting the derivative equal to 0. Right? And if I do that, well, that's just a quadratic equation now. So I can, in fact, this one factors. So I can pull an x out of here, and that gives me x times 3x minus 6 equals 0. This one will give me x equals 0, and this one gives me x equals 2. So these two things should be the zeros of our derivative. And if we look over here at the graph of this thing, and those are exactly where our zeros are. And you notice those zeros are what divide the positive and negative sections apart. So I'm negative here, I'm positive here, and I'm positive here, right? Now, we're telling this from the graph. We want to be able to do this without a graph, because the point of this is actually we're building up to being able to graph functions, any functions really. So what you end up doing from here, let's see, how can I do this nicely? I'll just do it over here. In fact, let's switch that to black. There we go. You create a number line and you start marking things on it. And you don't really have to have, you just want things in order more than anything else. They don't have to be nicely spaced. So I know I have a 0 here, I have a 2 here, right? And I have regions in between. And this is what you do when you don't have a graph. You need to figure out where this thing is positive and negative. Now, not all critical points comes from zeros of the function. Some of them come from where the function is undefined. So it is actually important to note the difference between these, that this one came from a 0, this one came from a 0, not from being undefined. Because undefined means something different. So we want to see whether we're positive or negative in each one of these regions. So what we do is just pick a number that's in that region and plug it in. So let's just start with the first one that's less than 0. So if x is less than 0, I can pick anything in that region. I know it's all going to be the same sign. That's all I care about is the sign right now. So I'm going to pick -1. So if we plug in -1 to the derivative, right, that's what we're looking for, is if the derivative is positive or negative. So if I plug in -1 and test it, I'm just going to test it on this part because that's going to be easier. That's going to be -1 for x on the outside, and then the inside piece here is going to be 3 times -1, so it's going to be -9 times -1, that's positive. Right? In fact, let me switch that color so we can see it better, because I know I'm running out of room here. So it's positive in this region. Between 0 and 2, I need to plug something in. So I'm just going to pick 1 because that's the easiest thing to plug in. Actually, let me clean that plus sign up. So I know I'm plus here. So if I plug in 1, I have 1 times Well, 3 minus 6 is negative 3. So 1 minus 3 is negative. So it's negative in here. And then the last piece, I'm going to plug in something that's clearly in there. I'm just going to pick 3 because it's in the neighborhood. Really, it's just picking the most convenient point, right? If you have a 0 to plug in a 0. So 3, that puts a 3 on the outside. I have 9 minus 6, which is 3. So 3 times 3 is 9. That makes it positive again. Okay, so what we have here are the regions of increasing and decreasing. So if it's increasing, and I'm just going to use this arrow up with a G for increasing, I know it's increasing on these intervals from 0 up to, I wrote that backwards. Try that again. From negative infinity up to 0, right? It's increasing in that interval. It's also increasing from 2 to positive infinity. And then it's decreasing from 0 to 2. Right? So the first thing you need to be able to do is identify the intervals that it's increasing or decreasing. Right? And this is basically the algebra for it. You just find the critical points and then test a point in between all of your critical points. If you are given endpoints, sometimes you are given endpoints, you have to test those as well. You have to mark those down on your number line and do that too. Okay, so what I want to do, I want to define a couple things that I haven't defined yet. We actually use them, but they're not necessary. They're just a definition of something. And then we'll look at another example here. So let's go ahead and select all, clean that off here. Okay, so definitions here. A function is monotonic on an interval it's a closed interval if f prime of x is greater than 0 for every x in that interval, or if f prime of x is less than 0 for every x in this interval. Right? So these are just basically, you're talking about something that's monotonic on an interval means it's either all decreasing or I went the wrong way with my arm. All decreasing or all increasing, right? That's basically what it is. There's no point where it changes from increasing to decreasing on that interval. Then it's a monotonic interval, right? This would be called, if the slope is greater than 0, this is monotonic increasing. And this is monotonic decreasing, right? So basically, this is just so we know what we're talking about. The word monotonic actually isn't used too much in this section. It's just kind of the general category of what we're looking at. We're looking at intervals of, for lack of a better word, monotonicness, I guess. So we're going to be doing that by looking at the derivative. Where the derivative is positive, it's increasing. Where the derivative is negative, it's decreasing. Where the derivative of 0, it's doing neither. All right, so let's take this whole process from beginning to end, and we'll actually start looking at how we can also use this maximum and, these monotonic intervals to find whether something is a maximum or a minimum, which is kind of nice. We can actually tell something about our critical points as well. Okay, so let's go ahead and take a look at another example here. Okay, so let's go ahead and get that example up here. So why is this not working? Try this one more time. There we go. Okay, so this is one of the ways you'll see this. Sometimes you don't have to actually do the derivative taking. you're handed a derivative. So f prime of x is equal to x cubed minus x squared over x plus 2. Okay, now, in order to do anything with this, to tell where it's increasing, where it's decreasing, or anything like that, we have to be able to find the critical points. Right, so let's go ahead and list those, and then we'll get them on some sort of number line, and then we'll start checking our intervals. Okay, so critical points. Any critical points are found where either the derivative is equal to 0 or it's undefined. So when you have a rational expression like this, the derivative is equal to 0 when the numerator is equal to 0, right? And the denominator is not, so it can't cancel out the denominator. So let's make sure we don't have any holes in this thing. So if we factor this out, hang on, that was supposed to be a square. There we go. So if we factor this, we get x squared times x minus 1 equals 0. And then from here, I can see, well, either x squared equals 0 or x plus 1 equals, or x minus 1 equals 0. One of those two things has to happen. So we have zeros at x equals 1 and x equals 0. And those come from zeros, right? Okay, so now we have to see where it's undefined, and it's going to be undefined when the denominator is equal to 0. Well, if x plus 2 is 0, that means I'm undefined at x equals negative 2, right? Okay, so now we have x equals negative 2, and that's undefined. Right, and so I'm noting the difference between how I found these critical points, because they may or may, well, that will be important, actually. So let's go ahead and look at a number line. So let's go ahead and draw in a number line, and we'll mark all of this on here. So we got negative 2, 0, and 1. So we have 3 regions here. And I know that the 0 at 0 came from a 0 of the function. So did the 1, but the negative 2 came from undefined. So you can use whatever notation you want, but you do need to know the difference between when a critical point is found from being a 0 and found from being undefined. Okay, now we have to figure out what the signs are in between these things. Okay, so I'm just going to start all the way over to the left, and I'm just going to write the evaluation point I'm picking. So here I'm going to go x equals negative 3. And what we have to do is you just plug it into the function and look at what sign it is, right? So really you're looking at the sign of you're looking at the sign of f prime of negative 3. So if we go ahead and take the negative 3 and plug it into f prime, well, negative 3, and really we only care about the sign. So you notice what I'm going to do here is just keeping track of the sign of each factor as I go through this. In fact, I'm thinking it might be easier to look at it this way. Right, look at it in its factored form. So if negative 3, x squared makes the negative 3 positive. So it's a positive 9. Negative 3 minus 1 is negative. So the numerator is negative. It's a positive number times a negative number. And the denominator, if I plug a negative 3 in there, the denominator is negative. So I have a negative divided by a negative, which means that over here in this first region, I am positive, right? Okay, now we need to check over here. And so I think I'm going to use x equals negative 1 to check that one, because negative 1 is a real easy thing to plug in. And if we do that, negative 1 squared is positive. Negative 1 minus negative 1 is negative. And negative 1 plus 2 is negative. Right? So I have negative 1 plus 2 is positive. I said that backwards. That's a positive number. So it's a negative divided by a positive, which means that this interval in the second piece is negative, right? Okay, over here, with this interval between 0 and 1, I'm just going to pick, oops, let's do it. Try to keep my colors matched. X equals 1/2, right? And again, you don't have to have the exact value. You just need to know the sign. So it's a matter of working out the sign. This one, being a fraction, might be a little bit tougher, but it's still about the sign. So just look at each factor if it's positive or negative. 1/2 squared is positive, right? So I'm just going to write a positive. 1/2 minus 1 is negative. 1/2 plus 2 is positive. So this is, I think this is probably a little better way of seeing what I was doing in my head with the other ones. I'm just looking at the sign of each factor as I go. So that means I have a negative divided by a positive, which means that this region is also negative. So I have two negatives here, right next to each other. And then over here, greater than 1, I need to check that region as well. And so I'm going to use x equals 2 for that. Oh, I meant to do that. Right? So we have x equals 2 in that last region, that fourth region. And we just need to plug that in. So we found that was negative. And so now I need f prime of 2. And let's see here. 2 squared is positive. 2 minus 1 is positive. And 2 plus 2 is positive. So it's positive in this last region. Now, this is where it becomes important. Well, let me actually finish writing down the intervals. You're going to be asked for the intervals, the open intervals where it's increasing. Or open intervals where it's decreasing. If you're going to do that, what that means is you have an interval here from negative infinity up to -2. Here, now this is where they fudge the definition a little bit. And I'll talk a little bit about that after we finish this problem. This second interval, there is a 0 in the middle where it's not negative, but it's negative on both sides. So we still say that the interval that it's decreasing goes from -2 all the way up to 1. And then lastly, the last interval goes from 1 to infinity. Right? Now, what I was talking about fudging the definition, because it really says, the definition that they give you in this book says that the interval of increasing is where it's strictly positive. The interval where it's decreasing is where it's strictly negative. Now, not every book gives that definition that way. So you have to kind of be careful. And I think that's why they ask for open intervals, because you can omit the endpoints if they're undefined. But when you have two negative ones back to back here, you got something going on in the middle where it's not increasing and not decreasing, even if it's just undefined. Okay, so these would be the intervals. It's increasing on this interval, it's decreasing on this interval, and it's increasing on this interval. Right? Now, there's also a way to tell if you have a local maximum or minimum. Right? You know that the local maxes or mins are going to be at critical points, but not the ones where it's undefined, if there's an asymptote anyways. And this one, because it is an asymptote, because that undefinedness is being caused by division by 0, right? And it's not a removable discontinuity. So that means that this is not going to be a max or a min in this particular case. However, these other two zeros might, right? And so if a function is decreasing and then it decreases again, it's not at a maximum or a minimum. But if a function is decreasing and then it increases, that's going to be a minimum. If a function is increasing and then it starts to decrease, you're going to have a maximum, right? And these are local maximums, but you can actually look at, in fact, let me clean this up a little bit here, just so we can look just at this interval here. In fact, let me just do it this way. I'm going to redraw a number line just so we can see just the number line. So that was at, I think that was -2, 0, 1, and then we had plus, minus, minus, plus. That's the only part I want to take a look at. Okay, so this was undefined, right? And this is actually an asymptote. So we don't have to worry about that being a max or a min. Now this, the function is decreasing, right? This says it's decreasing. And then there's a point where the slope is 0. Ugh. Let's try this again. So the function's decreasing. There's a point in here where the slope is 0, and then it decreases some more. And so what that means is that this is not a maximum or a minimum. It's not an extrema of any sort. This one, though, you know, notice it goes from being negative here to positive here, which means that the slope is negative first, and then it flattens out, and then it starts being positive, right? I have positive slopes on this side, I have negative slopes on this side, which means there has to be a local minimum. It may be an absolute minimum, right? You find that out the same way you found out if something was an absolute minimum before. You plugged it in. Now, we have a little bit different thing going on here because we're talking about polynomials and rational expressions and things like that. So if the function ends up going off forever in one direction or the other, you may not have any absolute maximums or absolute minimums. So you just have to kind of poke through it until you find your answer. And this is one of those things, it's very, in fact, let me do this. I just want to step out here. It's very difficult to try to put these things together sometimes because of the fact that there are so many little pieces, and we actually didn't learn any new techniques. We learned about interpreting the techniques that we already have, right? How the techniques we already know will give us more information. And so that's the practice we're going to be getting. Now, there's no way I can, you know, itemize the thought process on this because every problem is different. The things that are always the same is that critical points are where the function changes from increasing to decreasing. Now, that's the biggest thing that we're talking about here, right? What information does that give us? Right, so we're looking for periods where they're increasing, periods where they're decreasing, and you just kind of have to keep poking at it till you find it. So I do absolutely expect questions on this. This is one of those things where everybody thinks about it a little bit differently, and so helping you understand it if you're having difficulty, I'm going to need to communicate with you. So if you're having difficulty, please come and see me, especially with the next exam coming up. So in any case, until next time, keep your pencils and your wits sharp.